Good afternoon, everyone. My name is Eran, and I'm a software engineer. We haven't started the presentation yet, so I'll wait a bit. Okay. This is not my presentation. It's on the browser.
The browser?
Yeah. Yeah, but that's this. Because the fonts got mixed up. Thanks, and I think they... Thank you. I don't know your name. Sorry. Sergey. Hi. I can see it. Sorry. Helps me loosen up, though. Okay, so I'll introduce myself. I'm a software engineer at Intel. I'm actually fairly excited to be here, as I did my bachelor here around 10 years ago, and so it's an honor to come back as a speaker. I'm a senior software engineer at the Advanced Analytics Group at Intel. At Advanced Analytics, we're composed of approximately 150 personnel, from data scientists to machine learning engineers and product managers. And we are all here in Israel. And it's the arrow. Okay, so I'll just come here. I'll click. It's okay. So we develop machine learning and artificial intelligence solution across many Intel divisions, from hardware validation to sales and marketing. Some of our solutions are even outside the company, such as the health project, specifically Parkinson, which are deployed outside of the company as well. I've been working there for the past 7 years, and today I want to talk about one of our solutions that we recently deployed for video analysis, actually serving in real-time deep learning models. A little bit about video analysis. As we all know, it's been received a lot of attention lately, mainly because of the adaptation and involvement or improvement in deep learning. And there are some core challenges there that people aim to solve because they help many use cases in reality, be that segmentation of images or videos, skeleton identification of movement of joints, or detection recognition of regions of the video or images. Even video captioning, which is really cool. Most of you probably seen it, describing what the user may exhibit in the video automatically. And since these are getting a lot of focus research-wise, they're getting a lot of focus from the industry as well. Efforts in making those models lighter, compress them, prune them, deploy certain ones on edge devices such as smart cameras, and getting inference really fast in real time. Our motivation, though, was a little bit different. We were expected to automate visual inspections. Each one of the units manufactured at Intel goes through a validation process. During this validation process, there are labs that are in charge of performing visual inspections on those tests running on those using units to detect defects or dynamic system outputs, defects and maybe some anomalies. We were requested to receive feeds of video cameras that would stand where a human would usually stand and report those defects and anomalies on those live system outputs, which I cannot go much into it because it's patent pending and stuff, so that's all the mystery. And report the findings to the engineers. After examining this, let's say, unique problem, unique use case, we came to realize that we had another few more challenges on our hands. First of all, different defects may come from very different worlds, may require several models, several deep neural networks to go through just to detect a single test that would indicate few defects, since they're not from, let's say, a specific problem. The second thing is, while in video understanding, many of the problem you can assume some kind of smoothness meaning if the car drives straight, then in the next few milliseconds it would continue to go straight, so you can maybe downscale your video a bit and still get good results. In our case, since we are expected to identify anomalies as well, we were expected to go through each one of the frames in real time and running them through the network, so we had a lot of computation on our hands, and we needed to do that in real time. Those unique problems had a bit more challenges, since the customer told us, listen, we're going to stand cameras that's going to view the process and send you the feeds. You cannot deploy anything into the lab because this is not your lab, this is our lab and our process, so you cannot interfere, which made it a problem because if we, for instance, wanted to deploy smart cameras to do the inference faster, we couldn't. After reviewing all this, we've decided to deploy a solution that would centrally serve those video feeds with focus on low latency. And I put emphasis on low latency because usually you want your system to, specifically in deep learning, everybody is looking to maximize the throughput of how much inference they can do. So our focus was low latency, and not low latency for a single frame every time, but low latency continuously across all frames, all the video flowing through the system with consistency. So just to be clear what I'm talking about, how this thing looks like. So let's say we have a few video cameras spread around the lab, and they capture together around 100 frames per second. And they send their frames to our system. Our system runs each one of the frames through 3 convolutional neural networks, 2 LSTMs, let's say, and then takes all these 5 results for each one of the frames and does this reasoning process in order to get a final result for each one of the frames, presenting it to the end user. In this case, the end user got that one frame was flagged for a defect or an anomaly, for example. And we're able to do all this, and this is actually a small use case of what we previously done, and it is done in less than a second. So we got this sub-second latency of real time that we wanted. And we are able to do this because our system, as you will soon see, uses the lowest latency, the lowest possible inference time for each one of the models that it serves, even though I'm calling her she, it needs to serve a lot of frames, a lot of models. It gets the best inference time or the lowest latency inference time for each one of them. But deploying such a solution and developing it didn't come without operational or architectural challenges. So let's review those before we dive into the solution. So first of all, serving convolutional neural networks is hard in production. It's not like training them. You need to run a frame through the entire network, maybe several, and it takes time. And it's part of a critical path, and you're expected for a fast turnaround, react in real time. So that's the main challenge. The second thing is, if you're thinking about batching, which will increase your vectorization, parallelization of computation, which we usually do in training and in inference when we're aiming to maximize the throughput, then waiting for a batch to fill up will actually increase your latency. So we needed to know how we can use this batching mechanism without increasing the latency, use it for our favor. As I mentioned before, we had a variety of models. It's not just serving a single model fast. It's composing, assembling the result of several models and doing it as fast as possible. And as in any other system, you want your system to be scalable, meaning if today we have 4 cameras in one lab, tomorrow we have 1,000 cameras, we want just to add resources and be able to grow seamlessly. So what's the problem? Just as resources, but the question is how much resources and when? What is the criteria for scaling? And usually the criteria is, let's say, I'm going to say GPU, even though I work at Intel, GPU utilization. Okay, but if you're batching naively, then your GPU utilization fluctuates. It's idle sometimes, and sometimes it can reach 100%. So when exactly do you scale? We needed to answer that one as well. And I'm really thirsty, so I'm going to get a sip of water. Sorry. So without any further ado, internally we call it Archilon. This is a scalable, fault tolerance, and fully asynchronous serving system for video streams. So the asynchronous part sometimes comes as a surprise, but you're going to see how it helps us. The architecture is fairly simple. I hope you can see the shades of gray. Oh, that's not good. Okay, so it's very simple, composed of 4 main components. We got the API, the data store, the application, and the model. Now down here you can see the critical path. Nothing really interesting happens here. The cameras are sending the frames through the API, saved into the data store, Redis in our case. And then the findings are pulled from the data store through the API to the end user. Now the upper part is where the magic happens. The application pulling whatever frames it can find for processing, sends them for inference in the model part, get results and saves them. You can think of the application as a collection of asynchronous processes. And you can think of the model part as a collection of microservices, each one serving a specific deep learning model. Now this may look familiar to everybody who's working on software solutions in deep learning. This a little bit less. And the application part is what we're going to dive into. So the application, as I said, you can think of it as a collection of asynchronous processing units. And actually, this is our basic processing unit. We call them asynchronous inference unit, or an AIU. This unit is an always-on unit, always looking to process, always looking to utilize your resources. Not just wait, batch, and then GPU fluctuation, but utilization fluctuate, but constantly using the resources, creating this kind of dynamic batching. Let's see how this flow works. The AIU pulls frames from the data store. Whatever frames are waiting for processing, does some pre-process, sends them to their respective model. In this case, TensorFlow, it doesn't matter. Get the results, does some post-processing, and save the final results into the data store. Once it's done, it looks for other frames to be there. Now, as you can understand, it will find maybe a different number, so that's why dynamic batching. Now, in reality, what we see, and I will show a little bit later, is that this batch size actually converges to somewhat constant size of the optimal batch that would give you the lowest latency, given your resources. The unit is also stateless, which makes it by nature fault tolerance and scalable since it's also asynchronous, so you can deploy multiple units if you need more processing. On top of all these benefits, we got 2 more. The first one is really good separation of concerns. You can dedicate an AIU for any model you want to inference. And I say that because, for instance, here we got an AIU dedicated for ResNet, which converges to a batch size which is optimal for real-time inference on ResNet, and the other one for object detection. And this separation of concerns really helps us in getting the lowest latency possible for any given deep learning model, be it in PyTorch, TensorFlow, or else. The second benefit is the AIU is asynchronous and is agnostic to which streams it's working on. It pulls frames from different streams and batch them together, so it uses the batching mechanism in order to reduce the latency, because it gets better throughput in little time. So that's another benefit. The question still remains when to scale. Now this was a hard problem if we were batching statically, like waiting for a batch to fill up. But using the AIUs, this became a much easier question to answer. We've seen that most of our criteria are actually the 3 main criteria, GPU utilization, batch size, and latency, somewhat converges into a constant range due to any certain throughput. Meaning if there's a 30 frame rate, then these are quite constant. Now all that's left to do, according to operational needs, we need to decide, do we want to scale only when we're out of resources? Meaning we want to get the lowest latency possible given the resources we have now, then we will probably scale around here. But if we really care about latency, once we pass that latency that we care about, we can scale here and add the resources here or add more processes. So to conclude, I want to go through an entire flow similar to what I've seen showed before, but the entire one, it's a bit similar to a really small use case we just deployed. The cameras are setting the frames through the API to the data store. There is one AIU that handles object detection, does the post-processing, saves the results. Another one does the same for ResNet. And then there is a reasoning process which pulls the results, does some reasoning logic on it. In this case, it's an OR logic between the vector of results for each one of the frames and save them back to the data store to be sent back to the end user. So this was my solution, and these are AIUs, and open to questions.
Thank you very much. Any questions?
Okay, I can ask without it.
I like your hair.
How did you differentiate? Yes, thanks. How did you differentiate between which pictures will be sent to which model, or each model?
Usually,
by every picture?
yeah, in that, the logic is, let's say, constant for an entire deployment of solution. Meaning, we define in advance which models each frame that comes from that specific account would go through. But you can deploy it, since all of these are, this is a very asynchronous system, and all of it, I didn't mention it, but all of it is containerized and can be deployed very easily. You can deploy several systems for different logics if you need it.
What is your future direction of your research?
Wow, I didn't hear.
My question is, what is the direction of your future research?
Future research? Well,
What are you planning?
what I'm planning to do with
In
this?
what direction will you continue your research?
I don't know. Actually, this is a solution that was delivered according to need. The system is generic, and we're going to use it in other use cases, but we still don't know. There is no active research on how to, I don't know, make this system more robust for any reason.
Okay, let's thank the speaker again. Oh. Okay, our next speaker is Jan Pelek, who's